Today we will discuss the topic of nested quantifiers, section 1.5. Meaning of nested quantifiers. Nested quantifiers is an event that occurs when one quantifier is within the scope of another one. Examples of nested quantifiers are listed below. A, for all x, say x is a real number. For all real number x, there is a real number y such that x plus y is equal to 0. B, there is a real number y such that for all real number x, x plus y is equal to 0. Nested quantifiers appears a lot in mathematics and in computer science. Example 1. Assume that the domain for the variable x and y consists of all real numbers. So say x and y are real numbers. So now you are asked to find the meaning of the expression for all x, for all y, x plus y is equal to y plus x. So the solution of this statement, it says that x plus y is equal to y plus x for all real numbers x and y. What is the meaning of the statement? For all x, there is a y such that x plus y is equal to 0. It says that the solution, it says that for every real number x, there is a real number y such that x plus y is equal to 0. Example 2. The task here is to translate a mathematical expression that involves nested quantifiers into English. So consider that x and y are real numbers. So it says for all x and for all y, where x is greater than 0 and y is less than 0. That means x is positive number and y is negative number. So this statement that x and y all together means this implies that x times y is always going to be a negative number. Well, we know for sure that when you multiply a positive number with a negative number, you get a negative number. Okay, so we want to translate that into this mathematical expression into English terms. This statement says that for every real number x and for every real number y, if x is greater than 0 and y is less than 0, then the multiplication of both x and y would always be a negative number. The order of quantifiers. Does the order of nested quantifiers matters? Does the order matters? If you have two quantifiers, existential quantifier or universal quantifier, does the order matters? Yes, it does matter. However, the order of universal quantifiers alone, if you have nested two universal quantifiers or three universal quantifiers, the order does not matter. Also, if you have two existential quantifiers that are nested, or 3 or 4, the order doesn't matter. However, the order does matter if you have an existential quantifier and the universal quantifier. So the order matters when you have nested different types of quantifiers. Example 3. Let q of x denote x plus y is equal to 0. So what are the truth values of the following quantification? Existential quantifier y, universal quantifier x, q of x. And another statement, universal quantifier x followed by existential quantifier y, q of x. The domain here consists of all real numbers. So solution. The first statement, which involved the existential quantifier followed by y, universal quantifier followed by x, q of x. So this means there is a real number y such that for every real number x, q of x is true. It means that no matter what value of y is chosen, okay, there is only one value of x for which x plus y is equal to 0. That's false. The other statement, the second statement, you have the universal quantifier followed by x, existential quantifier followed by y, and then q of x. What does that mean? This means for every real number x, there is a real number y such that q of x, or such that x plus y is equal to 0. It means that given a real number x, there is a real number y such that x plus y is equal to 0. Yeah, that's a true statement. Example 4. Let q, x, y, z be the statement. X plus y is equal to z. So what are the truth values of the following two statements? The first statement, universal quantifier x, universal quantifier y, existential quantifier z, q of x, y, z. The second one, an existential quantifier z, universal quantifier x, universal quantifier y, and q, x, y, z, where the domain of all these variables are real numbers. The first statement means for all real numbers x and for all real numbers y, there is a real number z such that x plus y is equal to z. That is true statement. The second one means that there is a real number z such that for all real numbers x and for all real numbers y, x plus y, z is true. This is a false statement. So in the following table, you see what happens when we negate a nested quantifiers. So when we apply a negation for universal, the universal quantifier become existential. When we negate an existential quantifier, it becomes universal. Example 5. Determine whether the argument given here is valid, and determine whether its conclusion must be true because of the validity of the argument. If square root of 2 is greater than 3, then square root of 2 squared is greater than 9 over 4. Let P be the proposition square root of 2 is greater than 3 over 2, and Q the proposition square root of 2 is greater than 9 over 4. This argument is valid because it was constructed using modus ponens, a valid argument form. However, the premise here is false. Therefore, we cannot conclude that the conclusion is true. Here are the references we use to make this presentation.